All right. Hey everyone. So we're just going to continue on with our discussion of the second law of thermodynamics and how it plays into something called entropy. So as you may have heard, we talked about a thing about, you probably heard about entropy as a phrase referring to the amount of disorder within a system. Um, so we're going to be talking about that. Now, one thing that we want to mention though is entropy, much like potential energy, while it does have an absolute value, it's not really super important, not really a relative number. What we normally want to care about is the change in entropy, just like how we care about the change in potential. Um, Now, I'm going to go into detail a little bit later on about what I mean by disorder, because you probably heard the term of disorder, but not really known what it meant. So what we're going to use is we're going to use the symbol S to represent the entropy within a system, and Q being the heat added to the system by a reversible process. Now, when the temperature is constant, what we end up getting is this, that the change in entropy is going to be equal to the amount of heat added to the system divided by T. One thing to note is that we can also kind of use this equation for very small changes in temperature. Um, we'll come up with an equation later on of what you should be using when you have much larger differences in temperatures, but for the most part, this could be used for any situation where the temperature remains the same or changes by very little. Now, if we do have a varying heat, temperature, uh, and entropy, we would use this. So this would be kind of like our calculus-based form of the equation. We're going to end up using this in order to figure out a much better equation for much larger changes in temperatures. All right, and that's done by basically taking this and taking the integral of it. So like I said, we're going to do this later on. So normally what you do is if when you do want to find the change in entropy, you can use this and take the entropy from A to B. If the temperature is the same, then you end up getting this equation like we got last time. But because Q technically is somewhat temperature dependent, what we would do is bring in the equation that relates Q and T into here to find the this equation for what the change in entropy is. All right, so what we're going to do here, pause the video, you can work on this yourself, and we'll go over in a second. All right, now what you can do, we have two samples of water being mixed together. We can do some math, the calorimetry stuff, in order to figure out where the final temperature is. But realistically, we could just look at it and know where it's going to end up. Both samples are equal mass, and they're both water, so it's going to come together at the middle of the two temperatures. So between 20 and 24, the final temperature is going to be 22 degrees Celsius. One thing I forgot to mention about the temperature is that the temperature in that equation is in Kelvin. Remember, the only time you're allowed to keep something in Celsius is when you're doing a change in temperature. All right, so what we're going to do is we're going to figure out how much energy was actually gained and lost by the samples of water by using MC delta T and figuring out how much energy it is. So plug in our numbers. Again, it's going to the middle temperature. So it's going to be ending at 22 degrees Celsius. And we end up getting this as the temperature lost, but it is also the temperature gained by the, oh, actually, yeah, so this is the temperature gained by the low source. This is also equal to the temperature lost by the hot source. So yeah, QH, what we would just do is make a minus because it lost this energy rather than gained it. So when we take our equation, that's what we're going to do. We're going to do QH over T and add it for the two samples. Now, what I'm doing here, you'll notice that there's a bar above these temperatures. That's because I'm saying I'm going to put in the average. So this water goes from 20 degrees to 22. So this temperature is 21 degrees Celsius. And then same thing, 24 to 22. this is 23 degrees Celsius. Because it's such a small change in temperature, I can just kind of do this because there's not going to be that much of a difference. So what we end up getting is this, that the change in entropy is about 9.62 joules per Kelvin. So we end up getting that the change in entropy does end up increasing when we mix these two samples of water. So even though they change their energy by the same amount, because of the fact that this one is at a hotter source, um, its entropy change isn't nearly as much as this one. So this one, which is at a lower temperature, changes much more because of it. So yeah, this is pretty interesting to note that both systems are, well, this system's decreasing, but not nearly as much as this cold one. And we end up getting the positive entropy, saying that the entropy is increasing. In a case like this, where so this is saying about the whole temperature going into the intermediate temperature, the middle temperature. What we can do is kind of take what we just did and apply it a little bit more generally. So when you have two systems that are isolated, where there's going to be heat flowing from one to the other, kind of like the calorimetry stuff, we'd end up getting this. This is supposed to be like the temperature from high to middle. So kind of what we did before, where you take the middle point, and this is from low to middle. In the case like this, where it's isolated, these heat values will be the same, so it could be pulled out, and you end up getting this. And because of the fact that THM is always going to be a higher number than TLM, what we end up getting is that this fraction is always going to be smaller than this fraction. So in an isolated system, the entropy will always end up being bigger than zero. This is a very important thing with the second law and with entropy, is that in isolated systems, the entropy is always going to increase. So now I'm going to go and show you how you would do it for more drastic temperature changes. So what we would do is we go back to this integration form of the equation, and what we're going to do is we're going to plug in MC delta T for Q. That way we can have a relationship that's related to this temperature. And we're going from the initial temperature to the final temperature. MC gets pulled out, so we're just integrating this, which means the equation will end up being an ln function. So we end up getting ln TF minus ln TI. We can combine these two ln terms by just dividing the inner parts, and we end up getting this. So this equation can be used when we have a much more drastic temperature difference. What you could do is you could try this for the other question. You'll find that you get pretty much the exact same number. So here, actually, we're going to do it real quick. So if I take the same scenario, we had the two samples of water, both at 50 kilograms. We use this equation. I could pull out the 50 and the specific heat because it's going to be the same for both. And what I do is I plug in the numbers for making sure that I convert it into Kelvin for the final temperature and its initial hot temperature and initial cold temperature. And what we're going to end up getting is 9.61. So very, very close to what we got before. Like I said, a very small difference. But as that temperature change gets bigger and bigger, this difference is going to become more noticeable. So typically, I would say that doing what we did in the previous question, we can do that for ranges of about 5, maybe 10 degrees. But anything more than that, you would want to try to do this, or else your number will start to kind of deviate more and more. All right, so what if there was no temperature change? What if instead there was a volume change? Well, we're going to consider an adiabatic expansion where it goes from some initial volume to some final volume. Now, if you recall, our change in Q was actually equal to this, P dV. That was one of the things about the adiabatic free expansion, was that Q was equal to dW. So what we end up getting is when we get this equation, we get dq, and then we plug in this equation, PdV. Then what we can do is we take the ideal gas law for P, plug it in so that we get a relationship related to volume change. Same thing, we integrate this, we get an ln function, and we get this nr ln of this volume ratio, which for an expansion will always end up being greater than zero. So we can do this for other different scenarios. Of course, you're going to want to make sure that you derive it based off of the scenario, but it's derived the same way. You come up with an equation that relates dq with something that's being changed, whether it's temperature or volume. You plug it into here, and then you integrate. And you want to make sure that you have variables that are together. So you kind of, if it's a gas at least, you could include things like the ideal gas law in order to kind of put that in as well. All right, here, so you can pause the video, work on this yourself. We'll go over it in a second. All right, so here, what we're going to do is for the iron, because it's going to have a much drastic change in temperature, it's going to go from 880 Kelvin to 280 Kelvin. I'm going to use the ln function, but for the lake, it's not going to have any change in temperature, so we're going to actually go simple for that one. So this is just me re-deriving the equation real quick. Typically on a test, I would like to see this, mainly because, like I said, you want to kind of prove that you can use MC ln T2 over T1 rather than just assuming that it works. So for the iron, the change in entropy, when we plug the numbers in, will end up getting me negative 1030. Now, in order to figure out the lake, I need to figure out how much heat was actually transferred to the lake. So I'm going to still look at the iron, do MC delta T for that, and see that it lost 540 kilojoules, which is how much the lake ends up gaining as well. So for the lake, we're just going to take this 540 and divide it by its constant temperature of 280, and we get 1930. So altogether, we end up getting that the total change in entropy is once again a positive value of 900 joules per Kelvin. So while the iron does decrease in entropy, the lake ends up increasing in entropy much more. So here, the entropy. This is kind of a big thing, that the entropy of an isolated system will never ever decrease. It will either stay constant, which is only going to be true for reversible processes, or increase, which is true for irreversible processes. Which, if you remember, these are real life scenarios. So pretty much in real life, it's always going to increase. It will never decrease. The only time it's constant in these is in the ideal cases. Now, I just want to point out that I just want to clarify that the entropy doesn't say that it never decreases. It's just that when we take into account all the changes in entropies that are being affected by one thing, you'll have a net increase, or it'll just be constant. So, like if you're looking at ice, as ice ends up freezing, technically there is a decrease in that entropy. However, if we take into account the entropy of the hot environment, well, then in that case, that one's gaining more entropy. So you end up getting an increase in total entropy. Okay, so from here, that total entropy, this is just repeating what I just said, that the total entropy will always increase due to any natural process. Yeah. Because of the fact that this actually ends up giving us an idea of how energy is supposed to be conserved and how the process has to go. A lot of times, entropy can sometimes be referred to times arrow. Like typically, a lot of laws that you'll see in physics will always just state that energy is conserved. Well, this one actually is one of the few ones that tells us how it has to be conserved. that it has to be conserved in a way that it's going from a increasing entropy, not a decreasing entropy. So it is pretty interesting that it works that way. Um, Yeah, so I just want to point out that this ends up becoming a huge thing later on. In fact, when you go into further topics of thermodynamics, you'll find out that there's so much more about entropy. We're basically just dipping our little tiny toe into the vast ocean that is thermodynamics and entropy, but we're just going to leave most of that stuff for later on. Um, so I wanted to talk a little bit about what entropy actually is. So going back to what we said before about how the entropy is always going to increase, that pretty much can be reworded as saying that any natural process will tend to move towards a state of greater disorder. Um, Now, what this ends up actually leading us to in the great grand scheme of the entire universe is that eventually we're going to end up experiencing what's called heat death. So, for those who don't know, if we kind of go back to what this is saying, uh, basically every time a process occurs, every time there's a change in energy, there's always going to be some energy that gets lost in the form of heat, exhaust heat to the environment. And that exhaust heat will always end up being unusable, essentially. What this means is every time as things exist longer and longer, people come and go, animals come and go, planets form and disassemble, and stars form and burn out. Every single time that something happens, a little bit of heat is lost, and that will never return. And as that continues more and more and more, the universe, the entropy of the universe, how much energy it has that's unusable, builds up and builds up until it gets to this point called heat death, where the entire universe is filled with unusable heat energy. Now, yeah, so I just that's what I kind of said before. So this actually ends up leading into a bunch of really unique theories about the universe. Of course, if you do know anything about astrotheory and the whole idea about the shapes of universes and the long-term effects of how of what is going to happen to us in the future, you'll know that this actually only applies if the universe is shaped a certain way. Though most scientists tend to see that this is the most likely outcome for humans. Of course, we might not be alive for that. It's going to take a long time for this to occur. Now, I don't know if I mentioned this later on, but there's a really, really interesting short story that kind of plays along with this idea of entropy and how it's always increasing and this lead to heat death. It's called The Last Question by Isaac Asimov. Very interesting story. You can see also find an animated comic about it, which kind of simplifies it because it is, despite it being a short story, it is also fairly long. What it does is it looks through the perspective of people throughout the age of the universe, and every single time a person at some point decides that they want to ask this supercomputer uh, it, what way they can decrease the entropy. Is there any way to reverse entropy? And it has a really interesting ending. I don't want to spoil it too much, but it has. I do like the theme that kind of keeps coming up about how in the very beginning, the people are just so nonchalant, whatever. Oh, we won't have to worry about that for another millions of years and billions of years. But then as the story goes on, the time starts to decrease more and more, and you can almost see the people. You can experience that the people are starting to get a little bit more agitated. Like, oh boy, it's gonna be 100 more years, and it's gonna happen. We gotta figure out how to change this quickly. So, uh, I think it's a pretty interesting theme, especially for us, since we tend to do the same thing. With things like climate change and fossil fuels, we always say, "Oh, we won't have to worry that for another 50 years, 100 years, and so on." But as the time starts to get closer and closer to it, we'll start to realize that that ended up being a very bad thing for us. All right, so you don't need to worry about this, but I want to actually explain a little bit about what we mean by disorder. Um, Now, what we have to do for this is we have to remember that in this topic, we're constantly doing things and talking about the micro states and how that's affecting the macro states. So, micro state variables would be things like the position and velocity of all the particles within that system. And then the macro states would be the things that we actually can observe: the temperature, the pressure, the volume. It turns out that for each of these macro states, there are bunches of micro states that could pertain to them. And the more micro states that are available that could result in a combination of these macro states, the more disorder we would end up having. Um, so first, we're just going to imagine coins. So, for example, the macro states would be things like this. We could have four heads. We could have gotten three heads and one tail, two heads and two tails, one head and three tails, or four tails. Now, the possible micro states, we're going to assume that each of the coins are their own unique thing. Well, for the four heads and the four tails, well, there is only one possible microstate: all heads, all tails. So this would be something that we would consider to be very organized, low disorder. Because if someone tells you that you got four heads, well, we know which ones are the heads. We know that all four of them are heads. Boom, easy peasy. But when you have something like this, three heads and one tail, well, now we have more microstates because either the last one could have been tails, the third one, the second one, or the first one. So that means there's four different choices that we can have for this. And then likewise, so this one's more disordered, and then we can go with two heads and two tails, which ends up peaking at about six possible microstates. So these are all the different combinations that each coin can have in order to come up with that same two heads, two tails. So another way of thinking about this is that you can think of this as being like if you were told a macro state and you had to guess which ones were tails. The more, the closer you are to something like this, the less of a chance you have, which means the sample is more disordered. If that makes more sense. So, like in a case like this, you pretty much have a 1 in 6 chance of guessing the correct combination of which ones are tails. But for things like four heads and four tails, you're guaranteed to get that. You have a 100% chance. This is, of course, assuming that each microstate state is equally probable, but that's what we're pretty much going to, in a lot of our cases, going to assume. Now, we'll look at a case with 100 coins to kind of see how that builds. For the most part, for 100 coins, we can find the number of microstates available by taking 2, because there's only 2 choices, heads or tails, and raising it to the power of 100. And we end up getting this total number of microstates. So 1.3 times 10 to the 30. It's extremely, um, it's an extremely high number. Um, yeah. So here's just another example. So again, like if I told you that you had that I gained 50 heads and 50 tails, and then asked you to guess which ones were tails, there are this number of microstates. So the possibility of you actually guessing the correct state would be 1 out of this number, which is an extremely small chance. Um, yeah. So I just wanted to point that out there. Um, yeah. So and then if you were to do this, the other thing this says about probability. So the thing that's interesting is that this one is the most likely probable, but in real life cases, getting exactly 50 heads and 50 tails is a little bit on the tougher side. It actually won't be as easy. It turns out that getting somewhere between 45 to 55 of heads will actually give you a much greater range, and you most likely get it within 70%. But as you get further and further away to this middle section where you get less and less microstates, the probability of getting to there is actually much more unlikely. So hopefully that kind of gives you a little bit better of an idea of what we mean by more disorder. And when we say that, like, oh, the entropy is high, so it's more chaotic, it usually means that the particles are doing a whole lot more stuff that makes it hard for us to kind of have an idea of what exactly the particles are doing. So thinking about like phases, for example, when you have a gas is much more chaotic. There are particles everywhere within that area, in that volume. They're moving in all different speeds, all different directions, all different velocities. But when you have a solid, they're much more organized. They're layered together, they're linked together. They may be moving, and it may be hard for us to identify how they're moving within that solid, but at least it's a little bit easier for us to figure out than the gas. So this kind of actually looks back to a distribution. Like, what would it mean for a system to be disorganized versus organized? So if you recall, we had the Maxwell distribution for a gas, and this is actually what we would normally get. So it ends up peaking somewhere in the middle, and then it slows down. Because there are so many particles that have such a variety of speeds, everywhere from 0 to essentially infinite, this would be a very chaotic, disorganized scenario. But if, on the other hand, we had it peak, so like here, this width, this range of speeds is much smaller than this. So this would be considered very organized. Uh, so yeah. Now, if you recall, we actually can't really get something like this when the speed is here, because this graph always has to start at 0. So that's one of the reasons why the speed or the organization is actually somewhat temperature dependent. I don't want to mention it right here, but yeah. So yeah, this is just kind of saying that, asking like, well, what's the likelihood of actually getting a very specific microstate if you have a ton of them? And it basically says like you'd have to wait until the end of the universe and you still wouldn't see it in a lot of cases. Now, when we actually talk about these probability of states, and we are looking at these like microstates and how how it plays with the entropy, there actually is an equation. It's given by this k ln of w, where w is being used to represent the number of microstates based off of a thermodynamic probability. So again, the bigger this is, the bigger the entropy is. But again, what we normally care about is the change in entropy when it goes from one state to another. So I'm pretty much going to skip it down to here. But one thing, so here is the thing, is that I said before that temperature does play a part into the entropy of a system. The lower the temperature, typically the more organized the system ends up becoming. And what we end up finding is that when we get to absolute 0, which realistically is not possible and it becomes harder and harder as we get closer, but if we can get a temperature to absolute 0, then the number of microstates actually does devolve into being 1 essentially. So yeah. Now the third law of thermodynamics kind of goes back to, it's something similar to the second law. Basically says that there's no engine that could be 100 efficiency, because if we look at the Carnot efficiency, this can only be true if this is equal to 0. But since we can never actually have the exhaust temperature being equal to 0, TL will always end up being some number greater than it. So we should always have a number that's slightly, at least slightly less than 100%. All right, so actually, this is where I mentioned before about the whole last question. I do kind of recommend reading it. It is a very interesting story. I like it a lot. Like I said, it has a very nice twist. Um, I don't know if the comic version has the exact same twist as the story, but I do recommend looking at that. And then this kind of just goes through what I was saying before, talking about stuff like the how to find efficiency or coefficient of performance, things like with entropy, all that good stuff. All right. So the homework. This is a typo. The homework is due Friday. It's going to be on chapters for chapter 20. It will be based off of these questions. So, as you'll notice, a little bit about entropy and Carnot engines, focusing mainly on it. Fridges and heat pumps kind of act like engines, so you don't have to worry too much about that. All right. If you have any questions, please feel free to let me know. Ask me in the sessions. Otherwise, see you in the next one.